interest for you.
We present a framework for the visual exploration of spine simulation data. We show the force distribution on spinal discs, enable assessments of imbalances, and reveal impact vectors that were not accessible before. This is a novel direction in medical visualization, and we hope that it might bridge the gap between biomechanical research and clinical application.
In cancer research, it's useful to group patients based on disease spread patterns to the lymph nodes. But once we create a new clustering methodology using spatial data, how do we explain spatial clustering to non-experts? In this multi-year project, we dealt with both a participatory design stage and a broader dissemination stage, and distilled specific lessons for interpreting spatial clusters.
Different sampling strategies have different performances in preserving features, but which one is the best? In this paper, we selected 7 sampling strategies along with 8 representative datasets and 3 important visual factors. We formulated 4 hypotheses and conducted a user study with 100 participants. For the derived insights, please refer to our paper.
Traditional flow visualization methods, such as the line integral convolution, convey information about the underlying flow structure. However, the influence of regions in the flow on each other is not visualized. In my talk, I will present a new dense flow visualization technique, creating a multi-level hierarchy that provides insight into the region's connectivity using a probabilistic model. For more specific details, come to my talk.
Given a dimensionality reduction scatter plot, we project its original subspace. Through the orientation and shape of our glyphs, both the global trends and local patterns can be identified. To transform the vectors, we use implicit function theorem. We apply our method to different kinds of data.
We present our work on data visualization, a technique which helps facilitate understanding of physical measurements and quantities by providing visible experiences to users in virtual reality. This allows them to experience the ground truth of what the data is in reality, as compared to the abstract nature of conventional data visualization. We hope our work will spur new considerations into how immersive technologies can be used for visualizing information, and that you will find it interesting.
Hello, everyone. Welcome to our VIS full paper session on guidelines and design spaces. Our first presenter is Xinhuan Shu, who will be telling us about what makes a Data-GIF understandable.
Hello, everyone. My name is Xinhuan Shu from the Hong Kong University of Science and Technology. Today, I'm pleased to introduce our work, What Makes a Data-GIF Understandable. Data-driven storytelling has been increasingly popular these years. A large palette of data stories have emerged and result in diverse genres in narrative visualization, such as infographics, comics, and videos. In parallel with these established genres, we see a recent rise of data GIFs online, especially on social media like Twitter. Here we show 3 typical examples from different sources. As we can see, GIFs are short animations with visualizations, played in automatic repetition, and focusing on a single core message. However, given the growing popularity, we lack an understanding of current data GIF design and usage. Existing works have studied design patterns and narrative structures for other data story forms like data comics and videos. Given the different visual properties, what factors are considered to create a data GIF? More importantly, it remains unclear how well people can perceive a data GIF, as animation is commonly questioned to preserve the context and track changes. And also Tamara suggests to give people the ability to manipulate the animation. Data GIFs, however, are on the other side. We are curious about how the data GIF design makes it understandable to the audience. So in this work, we start with a structured design space based on 108 data GIFs. We then conducted interviews and an online study to understand the effect of different designs from the perspective of viewers. Finally, we conclude with a set of design suggestions. Let's see the design space first. The collection of data GIFs are collected online mainly from the social media platforms and Google image search. The survey aims to span a wide range of visualization and animation designs to improve the diversity and exclude duplicate GIFs. Given the GIF property with a sequence of frames, we analyze the designs from 2 aspects, intra-frame and inter-frame. In the intra-frame designs, we consider the visual content in each frame, namely visualization types and narrative progress. As we can see, maps are mostly used in data GIFs, followed by line and bar charts. That is, basic charts almost dominate the GIF designs. Next, we introduce another factor in intra-frame design, narrative progress. Narrative progress describes how viewers identify the current playback progress. For example, the GIF shows how the COVID-19 spread across the US over time. It includes a supplemental line chart on the right top corner. The line chart shows the increasing number of the total cases and also indicates the GIF playing progress. But most data GIFs don't provide such designs. They just play the animation. While the true intra-frame designs examine the content in each frame, we then introduce the inter-frame designs, which capture the animated features that articulate the connection between frames. We introduce the following 3 factors one by one. First, the animation encoding. It considers the information encoded by the GIF playing progress. Since animation is widely used to track changes over time, we divided it into 2 categories, temporal and non-temporal. Multi-data GIFs in our collection convey a temporal process as well. Here is the same example as before. We further extract 3 different types of animations in non-temporal data GIFs. First is the faceting. It shows facets of a dataset in a series of frames, respectively. So this GIF is showing the curves of new cases in different countries, frame by frame. Narrative GIFs narrate a story during the animation, with highlighting, annotation, and text. Setup GIFs is like the creation animation, which animates the creation of a visualization. See this example. It shows that the bars are growing and finally presents the number of the total cases in multiple countries. The process and the speed don't encode any data. The second factor is context preservation. This factor examines the designs used to check the previous frames within a loop. We describe it regarding the extent of context preserved, namely no context preserved, partial context preserved, and entire context preserved. It is easy to imagine no context preserved method. The GIF only shows the current country in each frame, and no more information from other frames. For the entire context preserved, it should preserve data from all previous frames on the current frame. So in this GIF, the colored line is growing spirally, and the new growth overlays on the previous ones. We found 3 different designs in partial context preservation. They are baseline, trails, and overview. Baseline designs preserve the content in the first frame as a baseline during the animation, like the blue line in the GIF, which shows the distribution of the first year, so it is easy for comparison during the animation. Trails shows the trajectory of the data movement. In this example, each point leaves a gray trail when it is moving. Overview designs means the GIF presents a summary of data during the animation. The gray point here foreshows the upcoming points, thus providing an overview of the whole data. The final factor in the interframe design is repetition. It examines the between-loop design, describing what happens after the GIF is played once. We found 3 different methods to end the loop and start a new one. The first we call the loop. That is, the GIF directly starts a new loop once the last loop ends, so they do not have obvious designs that enable viewers to identify the end or the start of a certain loop. Next is pause. Some data GIFs deliberately pause a while before starting the new one, and form a freeze at the last frame. A particular design is bouncing, where data GIFs play the animation once, and reverse it to the start state of the loop. It works similarly to chasing back the history. Informed by the design space, we conducted 2 user studies to answer our initial questions. What makes a data GIF understandable? In the study, we collected a subset of 20 of our collected real-world GIFs in order to reduce the study's complexity. Here is the frequency of each design in our 20 sample GIFs. Based on that, we conduct a qualitative study through semi-structured interviews with 18 participants, and an extensive online study with 100 participants. The studies collect a variety of data, including observation, viewers' descriptions, questionnaires, and subjective feedback. The results show that participants would watch most GIFs playing more than once. Viewers reported they would see the GIF repeated, since it was short and automatically replayed. The details and the analysis of the results can be found in our paper. The insights into the design factors are further summarized in the design suggestions. So let's see the design suggestions. First, use the animation to convey a temporal process. Our survey shows that most data GIFs are used to show changes over time. Our user study also found viewers tend to conflate frames with time, even for non-temporal GIFs, like the right GIF. It just animates the creation of the bar chart. But many participants thought the process and the speed of the animation shows the temporal information. However, it doesn't. Second, preserving previous data visually supports the comparison and identification of subtle trends. For example, the middle GIF uses trail designs. It tallies well with the data contact, the bird migration, so it is easier for viewers to understand the data. And the right GIF reviews the whole process. Some viewers found the temperature grows slowly at the first and grows fast at the end. Third, leverage the end frame of a GIF. End frame is expected to subsum important information, such as previous data or take-home messages, thus making the GIF memorable. Otherwise, they may not help the understanding. Like the right example, even if it paused at the end, it does not bring many benefits for deriving conclusions or recalling content. In our study, we found that viewers expect obvious prompt for the end of the loop. Finally, incorporating the narrative progress. It provides a preview and orientation within the GIF. Viewers prefer the narrative progress design could help them understand the playing progress. In summary, in this paper, we contribute a structured design space based on a corpus of data GIFs and conduct user studies. We finally summarize a set of design suggestions for creating more effective data GIFs. Future work can generalize our results on larger studies with controlled data GIFs, explore other metrics beyond understandability, and also develop authoring tools for data GIFs. For more information, here is the project website with our dataset public for future research. Thanks for listening. I'm happy to take any questions.
Let's everybody thank our presenter. We have one question already from Steve Haraz. Steve asks, the presentation didn't mention the results of the study. Were there any particular findings that are noteworthy? Also, is the per subject data available?
Okay, thanks for the question. And we have put our statistical results, also the per subject statistics on our supplemental materials and also on our web page. And for the first question about the particular findings, we think like we have found that the natural progress design. Actually, in our during our interview, we found that many participants would appreciate that they see the narrative progress during the GIF playing. But in our quantitative study, we found that there are no significant results show that the narrative progress helps the viewers understand the GIFs. So we think there may be something worth studying further.
The next question we have from Matthew Bremer. He says, looped animations are typical on Instagram, and news graphic orgs teams often have platform-specific style guides. Did your corpus draw from Instagram?
Currently, our GIFs are more collected from Twitter and Google image search, not from the Instagram. But I think it's a good suggestion that we can look for more examples from the Instagram. Thanks.
And then Jesse Witt asks, did you differentiate aesthetics and comprehension?
In our work, we emphasize the comprehension, not the aesthetics. Since in our questionnaire, we design the questions most for the understandability and not about the subjective for the aesthetics. So our paper is what makes the Data-GIF understandable. Currently, we may most focus on the comprehension, and we also think the aesthetics of GIFs is much worthy studying topics. Like we can see that most GIFs are engaging and will receive many likes in on social media like Twitter.
Thank you very much. All right, we have now our next presentation, which will be given by Alex Bigelow on guidelines for pursuing and revealing data abstractions.
Hi. I'm Alex Bigelow from the University of Arizona, and these critters and I are excited to present our VIS paper. The way that we think about data is really open-ended. If I gave the same data set to everybody watching this talk, we'd probably get a lot of different perspectives. Some of you might be more likely to think of the data in terms of points in space. Others might be more likely to think of data as a network. You could also think of most data sets in terms of set relationships. And no matter how you're thinking about the data set, on disk it might be something totally different like relational tables. These differences in data perspectives can matter a lot. We know that choosing a poor data abstraction in a design study introduces serious risks, such as building a system that doesn't actually support any real user needs. We also know that only considering one specific data abstraction can limit your creativity and influence your analysis. For example, as an undergrad, I once tried to use a force-directed layout as a really bad version of multidimensional scaling. And even though we eventually realized our mistake, it took weeks for everyone on the project to stop thinking about the data as this kind of network. On the flip side, considering alternative abstractions can have major creative benefits, like how the authors of Abyss Explorer reversed what they considered to be a node and what they considered to be an edge, and it led to some incredibly cool new network visualization techniques. So the way that you choose to think about your data is important, but there's still a lot that we don't know. In fact, we know so little about this that it's hard to even figure out where to start. Nebulous questions like, how malleable are data abstractions, aren't really the kind of thing that you can just drop into the scientific method and churn out knowledge. There have been recent calls in the visualization community to begin embracing different ways of knowing. In this case, with only a vague question, we can still engage in rigorous research, but what we do and what we contribute may feel a little bit different from the positivist research that we tend to see, or the kind of research where you're rigorously testing a hypothesis. Instead, our paper focuses on getting at better questions and discovering the blind spots in our own thinking. We want to describe phenomena for the purposes of generating and refining hypotheses. Our epistemological goals are interpretivist rather than positivist. To do this, we employ a technique called grounded theory. And as it hasn't shown up very much at VIS, here's a quick introduction to how it works. Although, for those of you that are familiar with grounded theory, please keep in mind that I am glossing over a lot for the sake of time. The general pattern of our grounded theory investigation involves identifying codes or specific observations of phenomena that arise while conducting various research activities. In our case, we engaged in theoretical discussions, performed ad hoc interviews, and conducted a survey. The choice of research activity is, in turn, informed by the codes as they evolve. As codes mature, they're typically grouped into categories and begin to form themes, or higher-level descriptions of phenomena. Eventually, codes and themes reach saturation, or a point at which researchers are confident that the codes and themes are unlikely to change very much, even if additional data were to be collected. This means that you've arrived at what is often called a substantive theory that describes phenomena with enough detail that it becomes much more straightforward to formulate hypotheses. And because it's grounded in real observations, you can have a better sense for whether the questions that you're asking will matter in the real world. In asking our how malleable is a data abstraction question, we wanted to learn from people who think a lot about both its theoretical and practical implications. To get a diverse group of perspectives, we focused on several different communities, including people from our local university, people at the VIS and supercomputing conferences last year, and we also decided early on to engage with a local meetup group that met bi-weekly at a coffee shop, at a bar, and online, in an informal setting where people frequently brought laptops and asked questions about their code or data. This group included a very diverse array of data concerns, from bioinformaticians, paleontologists, and linguists from the local university, to designers, developers, and even vehicle mechanics in the local community. The meetup group in particular facilitated opportunities for many ad hoc interviews in the context of a real project with real data. We also designed and deployed a survey with each of these groups. As is kind of unavoidable in a study like this, we went into these interviews with a specific data abstraction typology in mind, or a way to make sense of and categorize the kinds of data abstractions that exist. It didn't take many interviews for us to realize that it's actually pretty rare for a dataset to fit cleanly in one category. For example, even if someone has an Excel spreadsheet, it's really common for things like full sentences or even nested JSON to exist inside its cells. To call something strictly a table, strictly textual, or strictly grouped is usually a little inaccurate, but an abstraction typology still gives us a way to start asking more targeted questions. Early interviews show that introducing a typology can expose latent abstractions, or a data abstraction that's meaningful and useful, yet undiscovered. If, for example, someone thinks about their data spatially and they also think about their data as a table, what happens if you introduce a concept that they don't normally think about, such as groupings? We designed a survey to simulate the process of pursuing latent abstractions. Using an abstraction typology with 6 broad abstraction types, we asked participants to describe any dataset of their choosing in terms of the categories that were the best fit, as well as describing their data in terms of a category that they felt fit the least. This wasn't a typical survey. Remember, our goal wasn't a positivist test that could lead to statistically significant numbers. What we really wanted was to find the blind spots in our own thinking. We wanted better questions, so we added some mechanisms for participants to critique the questions that we were asking, as well as the language that we were using. Instead of just adding a comment field at the end, we made it possible for participants to skip entire sections that they felt had strayed too far from being relevant or useful. We also added an interactive glossary where participants could suggest alternative definitions and terms. We've released the full visualized corpus of survey results, and they're archived on osf.io. Although we're mostly focused on the malleability of data abstractions, we're hopeful that this data will be useful to studies beyond our own. There's one result, however, that we didn't report in the paper, and it's not in our released datasets. To incentivize participation in the survey, we gave away stuffed plushies. And there was some interest from the Viz community as to which animal was most popular. So, as a result, exclusive to this talk, we're happy to report that foxes and crocodiles were the most popular. So popular, in fact, that we had trouble keeping them stocked. Although we ran out of foxes first, this introduced enough uncertainty that this unfortunately means we're going to have to leave this very important question for future work. After analyzing our interviews and survey results, we ultimately arrived at 24 codes. We don't have time for them all, so here are just a couple highlights. Our 8th code is that many people did not feel that what they work with counts as data. This comment was really common when we asked people to take the survey. People were even sometimes hesitant to describe their Excel spreadsheets as data, and we weren't the only ones that noticed this. 3 of our interview participants independently made this observation while reflecting on their experiences working with people that are new to data science. One participant runs a regular data science workshop in the humanities, but it gets very low attendance. It usually has about the same 3 participants. As we talked about why it can be hard to convince people that they're working with data, he noted that seeing information as data may take a certain level of creativity and a willingness to experiment and fail. Our 13th code is that there's wide variation in how people describe hierarchies. We ran into this ourselves while designing our survey. Even among the authors, we recognized that someone could describe hierarchies as partitions of space, as a special kind of network, or as nested sets. We questioned whether a tree and a hierarchy are the same thing, but concluded that they have semantic differences. So in the survey, we deliberately paired hierarchies with networks, with the word hierarchy chosen deliberately to encourage feedback. And it worked. One participant commented, I find the separation of hierarchies and groupings to be a bit problematic for this domain. Many codes, such as diagnosis codes, exist in a hierarchy defined by metadata. However, it's quite common to refer to areas of this hierarchy as groupings. From these 24 specific codes, 4 major themes emerged. The first is that latent data abstractions are very common. Even people that are trained to look for latent abstractions, such as people in the VIS community, often miss opportunities to think about their data creatively. That said, the process of identifying an abstraction is an intervention with far-reaching effects. Although a lot can be gained by considering an alternative data abstraction, merely introducing a compelling new concept can have repercussions on the workflows and tools that people use, the science that they perform, and potentially how someone thinks. People have natural defenses against this invasive process. People are less willing to pursue latent data abstractions when the design of an existing abstraction is already fundamental to their workflow. One thing that seems to soften the blow is that introducing a data abstraction typology helps to focus reflection and communication about data abstractions at a level of detail that includes actionable information. As visualization researchers, we need to be transparent when we have an agenda, like when we want to identify data abstractions and associated tasks in a design study. Introducing an appropriate amount of theoretical background can, on its own, provoke creative thinking and help people to communicate things that they otherwise wouldn't. So what does all this mean for you? We've distilled the lessons from reflecting on our experiences as a list of 9 guidelines for pursuing latent data abstractions. Again, we don't have time to cover them all, so here's just one example. Create artifacts that document and convey abstraction details and demonstrate possible permutations. We discovered that even in discussion among the authors, there were times when we believed we were discussing the same abstraction, only to discover that we had completely different assumptions once we started drawing things or writing things down. Making ideas physical serves not only as a communication aid, but also as a method to explore the creative space of possible abstractions, as well as documentation for the decisions that you make. I'd just like to conclude with 2 parting thoughts. When you introduce a typology, one thing we discovered is that it's totally okay if it's imperfect. In fact, missing or inaccurate categories can be really useful because they can help people to engage with you at a theoretical level and explain important nuances about how they think about their data. That said, when you're preparing to discuss someone else's dataset, it's still worth the effort to try to prepare an explanation of the space of possible abstractions that's tailored for the person that you're talking to. For example, if someone has a rich mathematical background, the difference between physical space and an abstract mathematical space could be very important. But to someone else, that much jargon could be confusing and make them less likely to provide useful critique. One of the things that motivated this study was limited detail about data wrangling operations in published visualization research. We all do a lot of data wrangling, but rarely document the wrangling that we do as part of our publications. This isn't just important for reproducibility. Having more data about how we think about and work with data can teach us a lot. We're excited about recent efforts to recognize the reporting of data transformations as standalone research contributions, and expect that this will lead to better informed data wrangling tools and theoretical research. So that's about it. I'd like to thank my co-authors, our funding sources, and all of our participants, including many of you.
Let's everybody thank our speaker here. We have several questions in the chat. The first from Andrew Wenzel. Do you think that actively trying to frame data as multiple or unconventional types of data abstractions would be a useful step in the design process?
Yes, absolutely. This is one of the things that we even kind of saw in previous work as well of there's often this ideation problem that you have when you're creating a visualization that, oh, create 3 different versions of a visualization, and usually they're kind of similar. One way that you can really get something different is to introduce a different data abstraction. And this is, again, me kind of speculating that this is the effect, but I think that that would be a really effective creativity exercise to think about your data in a different way, and that can result in a totally different visualization design.
We have another question from Arvind. Fantastic work. I'm curious about the degree to which you have connected your thinking and work to distributed cognition, a la Hutchins et al.
We haven't at all, and we absolutely should. That is an excellent point and great for follow-up work. We should definitely do that.
Zipeng Liu has another question here. Do you have any thoughts about how to implement these guidelines? For example, I think it would be valuable to show examples of data abstraction permutation.
Okay. Like how to. So some of there are examples in the paper for how to do this to show, like, if I've understood the question correctly. One of the ways that you can explore these different permutations of data abstractions is when you're talking to someone about their data set, you give the kind of a quick tutorial about, like, here are the way that we think about data abstractions, these different ways, and then get them to respond and talk to them about that. I don't know if that answered the question, but.
There's plenty of other questions in the chat, but we can take those offline. Does everybody thank Alex again? Our next presentation is from Xi Chen, who will be presenting composition and configuration patterns in multiple view visualizations.
Hello everyone, welcome to the talk today. I'm from Shenzhen Institute of Advanced Technology, Chinese Academy of Sciences. The topic of my talk is composition and configuration patterns in multiple view visualizations. This is the collaboration's work with colleges from Bangor University and Tufts University. Thanks for all my collaborators here. First, I'd like to introduce the background of this work. What's the visualization process? The information visualization model states that visualizations are created in 4 steps. First, data transformation. Process raw data into data tables. Second, visual mappings. Map data tables into visual structures. Third, view transformation. Transform visual structures into views. Fourth, render and display views to users. But this is just for designing a single view. We see more and more multiple view visualization systems like this. In the process of designing multiple view visualization, we need to consider view type usages, position of a view, size of a view. This process is tedious and time-consuming. Sometimes the results fail to meet design guidelines. The visualization communities has contributed to multiple view visualization design from various perspectives, for instance, suggesting rules and guidelines, developing authoring tools, and automatically distributing multiple views in a visual space. However, thus much progress has been made. We still don't know what's the common practice in multiple view visualizations. For example, which view types are frequently used together? Where to position each view? What's the size of each view? This is an overview of our approach. First, we create a new dataset. Second, we conduct a series of quantitative analysis on dataset to find the patterns in design of multiple view visualization. Third, we combine the analysis into recommendation system to assist multiple view visualization designs. First, we need to define the properties of the views. There are 3 properties. First is the view type, such as bar chart, line chart. Second is bounding box, which are the center position, width, and height. Third, in order to distinguish small multiple, we treat the entire display space as the hierarchical result. After each view is coded, we then encode the overall multiple view visualization design. First, composition is considered as frequency, diversity, and correlations of view types. Second, configurations is considered as the position and size of bounding box. Based on the coding scheme, we collect 316 images from IEEE VIS, EuroVIS, and Pacific VIS publications. And we develop an annotation tool to label attributes of type and bounding box of each view. Then we refine bounding box annotations to remove the effect on manual annotations. After that, we create a new dataset. Based on the dataset, we conduct composition patterns analysis, configuration patterns analysis, and integrated composition and configuration patterns analysis, which are measured by conditional probabilities, usage frequency, and aspect ratio and relative position. Based on this analysis, we identify common practice around MVs. In the composition patterns analysis, this result shows that conditional probabilities of view types in columns, given other view types in rows, are employed in the MV. This shows that panel and bar chart are frequently used together with other view types. This value shows that view sign-based visualization incorporates bar charts. In configuration patterns analysis, we adopt code rule to encode the space arrangement of view layout in the display space. The numeric value represents the number of top-level views. The latter represents a specific type of layout. This is the result. This shows that most multiple view visualization design adopts simple layout. This shows that 2A occupies higher percentages in InfoVis and SignVis than the other three conferences. In the integrated composition and configuration patterns analysis, first is aspect ratio of 14 view types. This shows that the panels are typically vertically long and narrow. See this example. Second is relative position of each view type averaged from all multiple view visualizations. We are surprised to find that circle occupies much bigger space of about 25% compared to L and bar, which take up only 5%. From investigating, we can find that work on infographics design use circle chart to illustrate their approach. See this example. Third is the stability of each view type in the top 10 layout. This value shows that the map in layout 2A is rather stable, as we see most maps are positioned in the left rather than in the right. See this example. We combined our finding into a recommendation system. The system consists of exploration mode and design mode. Let me show the video. We can switch modes. In the exploration mode, we can filter by view type, number of views, and layout. The query result is shown on the right. On the top, coloring and grouping options are provided as a drop-down list. Detail of a MV is shown when hovering over the DOP. In the design mode, we can generate view by dragging, or adjust view size, or position, or align them together. We also can query similar MV designs with 3 views, and click Apply button, and to autofill. In conclusion, our contributions are as follows. First, we create a new dataset of 316 MV designs. The dataset is released at this site. Second, the study advances the community's understanding on view type associations and view layout arrangements. For instance, most MVs present less than 5 views. Third, the interactive recommendation system is developed that supports multifaceted exploration and recommendations of MV designs. And we conduct studies to evaluate the system. The evaluation result also shows that recommendation system can effectively help people design multiple view systems. Check out our papers for details, and welcome to our papers homepage. Thank you.
Let's everybody thank Xi Chen for her presentation.
Thank you.
We have 2 questions in the chat so far. Matthew Bremer asks, thanks for this clarification on MV patterns. Your corpus draws from visualization systems from the research community. Have you considered classifying and contrasting the MV patterns, public collections of visualizations by practitioners, such as Tableau Public, Power BI, Community Gallery?
Yeah, this is interesting question. We combine this to take it account to our future work.
I have another question.
Yeah.
I have another question for you. Can you tell me a bit more about the strategies you used for labeling multiple view visualizations?
Yeah, in fact, it's not easy to identify the visualization type of view. One, we cannot agree with each other. We use the majority voting method to ensure high quality. In the future, maybe visualization community can provide a clear classification of visualization type.
You also tried using automated labeling before you switched to doing manually labeling, but you had poor results with that. Are there ways that you can think of that this process could be better automated in the future?
Yeah, if more and more multiple view visualization data sets become available, people may be automatic labeled by data-driven deep learning.
And then last here, how might you extend the online tools that I put links to in the Discord chat here so that you can make recommendations based on information in the user's data set as well?
This is our limitation of our work. Our work doesn't take into account specific data and tasks. That's where we are going to work in the future.
All right, let's everybody thank her again.
Thank you.
Our next presentation will be given by Sehi, titled Comparative Layouts Revisited, Design Space, Guidelines, and Future Directions.
Hi, I'm Sehi from Harvard Medical School. In this presentation, I'm going to introduce our survey on comparative layout. Visual comparison is a common analytic task. For example, you may want to compare local characteristics in visualizations, such as estimating the delta of two bars. Or you can compare global characteristics, such as calculating mean values in individual bar charts and comparing them. To support such tasks, Hayder proposed three visualization arrangements called comparative layout. The first one is called juxtaposition, which is placing multiple visualizations next to each other. This is sometimes divided into two subcategories to differentiate the original juxtaposition from the temporal one. The temporal juxtaposition is showing multiple visualizations one by one over time, which is often referred to animated transition. The second layout is superposition, which is overlaying a visualization on top of the other. This is sometimes called see-through technique, since people commonly overlay semi-transparent visualization to see the difference. The last one is explicit encoding, which is directly showing the target relationship that people want to see. This includes showing not only the pre-computed values, as shown in this figure, but also includes showing any other relationship that users are interested in. These layouts are sometimes used together, which is called hybrid layout. For example, in addition to juxtaposing two bar charts, you can use an additional explicit encoding for visual linking or showing subtraction values. For the last decade, these layouts have been used in many applications, and their usefulness have been explored by many researchers through controlled user studies. However, we find it still unclear how to use them due to several challenges. We find that comparative layout have been used with inconsistent terms with confusion. For example, same visualizations are considered as either using juxtaposition or superposition across researchers. Moreover, our knowledge on comparative layout are fragmented across venues and papers so that we even observe conflating discussions. For example, juxtaposition is considered to be least effective for showing small difference in one paper, but it is said to be the most effective one in another. The goal of our work was to elevate the ambiguous boundaries to prevent any confusion and allow discussing their usefulness in a more consistent manner, and also distill the practical design implications based on the knowledge that researchers gained in the wild. To achieve these goals, we conducted a systemic survey on 127 research papers that employed comparative layout. These include 15 quantitative user study papers that compare the effectiveness of them. After analyzing survey results, we presented practical implications such as strengths and weaknesses of each layout, researchers' approaches to overcome the weaknesses, and actionable guidelines for using them. Through the survey, we observed many cases where same visualizations are indeed called differently across papers. Typical example is a grouped bar chart. It is sometimes considered as an example of juxtaposition because the bars are placed next to each other. But other researchers call this superposition because multiple visualizations are placed together in a single visualization. We suggested a lucid classification to elevate such the ambiguous boundaries. For example, we proposed to use an item-wise juxtaposition to differentiate it from chart-wise juxtaposition. We call it item-wise juxtaposition if visual elements, such as bars in bar charts or cells in heat maps, are placed next to each other. This separation of item-wise and chart-wise juxtaposition can be especially useful in discussing their effectiveness, because these two layouts showed quite different user side results according to our survey. Based on our classification, we observed diverse examples of using the layout. Here are several examples in bar charts and heat maps that covers the large design space of comparative layouts. These include chart-wise juxtaposition, item-wise juxtaposition with different arrangement, such as using a symmetric layout along certain axes, or arranging visualizations or visual elements along different directions. And also superposition, explicit encoding, and finally hybrid layout. The raw survey results, as well as an online gallery, is open to public, so please refer to the link below for more detailed information. After observing diverse examples, our main question was how to use comparative layout to more effectively support the comparison tasks. Toward answering this question, we distilled diverse design implications based on our survey. First, we summarize and offer the advantages and concerns of using each layout that researchers discussed in their paper. In brief, juxtaposition is the most straightforward approach, so it is easy to implement and intuitive to users, but it is likely to be less accurate in comparison tasks. Superposition can be more effective because comparison targets can be placed closer together, but it suffers from a major visualization problem, visual occlusion. Explicit encoding is considered to be most effective for supporting the predefined comparison tasks, but it hides important information from the original visualizations. For overcoming the concerns, one of the most common approaches that researchers took was using an additional layout together with the other one. For example, one paper presented an interactive feature to allow users to select a heat map to encode delta values with color in the rest of the heat maps. To overcome visual interference in superposed heat maps, one study allowed to pick visual summary upon paper folding interaction. Another study suggested to show grouped bar chart in addition to delta tick marks, so that original information can be still accessed to users. To build our understanding of comparative layout based on empirical evidence with actual users, we additionally analyzed 15 user study papers. Through this analysis, we identified consistent and contradictory results by making a visual summary. In this pairwise relation diagram, each node with different color represents a comparative layout, and arrows represent the significance of their effectiveness in performing comparison tasks. Blue and red edges represent that the corresponding pairwise relation is consistent or contradictory across studies. Those are placed in a way that the node on the top left showed the best performance, while the node on the bottom was the worst. We drew this diagram for each combination of different dependent variables, visualization types, and comparison tasks. Based on this visualization, as well as our survey results, we proposed design guidelines and promising future directions. In the rest of my presentation, I want to share some of the most important things that we gained in this analysis. When looking into local comparison tasks, such as comparing daytime bar charts or color difference in heat maps, chart-wise juxtaposition almost never outperformed any other layouts. Considering the diverse study settings, such as visualization types, task types, domains, and data, this seemed to be a very strong tendency. However, chart-wise juxtaposition sometimes showed comparable performance in a few studies. This happened only when proper visual linking is provided in the study design. One of the main difficulties in performing comparison tasks in juxtaposed visualization is that people have to find corresponding visual elements before actually comparing them, and this is error-prone and time-consuming. Visual linking looks to largely assist these subtasks according to our survey research. Hybrid layout was one of the most frequently observed layouts in our survey, and also was the most common approach that researchers took when trying to overcome the weaknesses that a single layout has. Study research also show practical evidence of the strong advantages that hybrid layout potentially have. When looking into the user studies that employed hybrid layout, they all showed some kind of superior performance of hybrid layout, such as their effectiveness in performing tasks, high preference by users, and better scalability. Lastly, user study research overall showed that the effectiveness of comparative layout are very sensitive to many factors, making inconsistent performance results across studies. This makes us reluctant to give clearer design guidelines of choosing the best layout for given tasks, data, and visualization types. For example, animated transition was the best layout in one user study, but it was the worst in the similar task but in a different visualization. Sometimes, even a single study showed diverging performance results depending on comparison tasks, as you can see many red edges in the diagrams. Moreover, using a same layout showed significantly different study results depending on each arrangement, such as whether to use symmetric layout in juxtaposition or not. Therefore, to be able to make more concrete design guidelines, we think we still need a better understanding of comparative layout by conducting more user studies and finding factors that separate the usefulness of the layout more consistently. If you are interested in learning more about comparative layout, please refer to our paper, our survey result, and also an online gallery for exploring their design space. Thank you for listening, and I'm open to take any questions.
Let's everybody thank our presenter. I have questions here. In the real world, not only the comparison tasks, but also any other tasks are performed simultaneously in a visualization. Have you also considered those aspects when discussing the usefulness of comparative layouts?
Yeah, so I think that is really a great question. So when you think about the visual analytics in the real world, we do not only try to support the comparison task, but also other tasks as well, because they are performed within the series of tasks in the real world. So in our paper, we try to suggest some discussion about trade-off between using comparative layout in that aspect as well. So Like for the more detailed information about that, please refer to our paper.
One more question I have for you. Were you able to categorize all of the visualization examples that you found from the survey into the design space you have?
So like we based our work based on the great original survey paper from Michael Glacier. And I think that is a really like powerful design space. They are already like based on like more than 100 research papers, 100 like visualization techniques. And in our survey, we were able to like annotate almost every like visualization examples within that design space with only few exceptions. Like some of the like interactive visualizations were kind of hard to like say if this is a juxtaposition or superposition, but there was only very few like examples, like up to 10 examples. So I would say like the coverage of the design space, I think is very effective.
Thank you very much, Sehi.
Thank you.
Our next presentation is going to be given by Paul Rosen on LineSmooth, an analytical framework for evaluating the effectiveness of smoothing techniques on line charts.
Hello, and thank you for tuning in to my talk. I'm Paul Rosen from the University of South Florida, and this work was done in collaboration with my PhD student, Ghulam, Jilani, Quadri. When visualizing data with line charts, as the data becomes large, it can get cluttered and noisy, making analysis difficult. For example, if I ask you, what are the most significant peaks in this data, you may have a hard time deciding which are truly important. To improve the presentation of the data, we can turn to data smoothing. However, in doing a quick search of the available smoothing methods, you'll discover there are many options available. Importantly, while the output of the techniques looks similar, each preserves different properties of the data. If we again ask, what are the most significant peaks? Your answer will vary greatly depending upon the smoothing method chosen. And so this leads us to two natural questions about smoothing. First, which smoothing method should I choose? And second, does it even matter which smoothing method I choose? Today, I hope to answer those questions for you. Up until now, the visualization community has lacked a work analyzing and classifying line chart smoothing methods. For this work, we hypothesized that the effectiveness of each smoothing technique depends upon two factors. The first factor is the nature of the data being smoothed. For example, the data may have long-term trends, cyclical behaviors, or high-frequency spikes that influence the smoothing results. The second factor is the set of visual analytics tasks that will be applied to the data. This work has the following contributions. First, we devise a taxonomy of 4 classes of line chart smoothing. I won't be discussing this taxonomy today, so please see our paper for details. Second, we construct an analytical framework for measuring the effectiveness of smoothing techniques under 8 different low-level visual analytics tasks. Third, we provide a method for ranking the effectiveness of various smoothing methods. And finally, we evaluate 12 smoothing methods across 80 datasets from 13 different categories. Let's begin by discussing the visual analytics tasks we consider. We selected a set of low-level tasks performed on line charts based upon Amar et al.'s low-level task taxonomy. We selected 8 visual analytics tasks, as seen here. Those include retrieving a value, which has the user estimate a specific value in the data. Determining the range, which has the user estimate the range of a specific set of values. Computing a derived value, which asks the user to perform an aggregation task, such as determining the average value. Finding extrema, which has the user identify peaks or valleys in the data. Finding anomalies, which has the user identify points that disrupt a trend. Characterizing a distribution, which has the user summarize a trend in the data. Sorting, which has the user order data by their relative values. And finally, clustering trends or points, which has the user grouping similar data together. We further group these tasks and devise analytical measures of the effectiveness of each. For example, the retrieve value and determine range tasks, we identified a measure we called total variation. Total variation uses the L1 and L infinity vector norms to measure the effectiveness. For the find extrema and find anomalies tasks, we measure the variation in the peaks and the valleys in the data. This is found using the Wasserstein and bottleneck distances of the critical points. For the compute derived value task, we use a measure of area preservation, which is the difference in the integrals of the input and smooth data. For the characterized distribution and clustering trends task, we use a measure called frequency preservation, which is an L2 norm of the frequency domain. Finally, for the sorting and clustering points tasks, we use a measure that we call value order preservation, which is based upon Pearson and Spearman correlations of the input and output data. You'll find the details of how all of these measures are calculated within our paper. Once our metrics were defined, we set about a method of comparing the effectiveness of different techniques. To do this, we devised a method for ranking the efficacy of methods either at a single level of smoothing for a single dataset, across all levels of smoothing for a single dataset, or across multiple datasets simultaneously. The resulting rankings are represented in a rank plot as seen to the right, where better ranked techniques appear towards the top. In this particular example, we rank the effectiveness of techniques across all smoothing levels for 6 individual datasets, and the overall performance for all 6 datasets. Once again, please see our paper for details about this calculation. Finally, we evaluate 12 commonly used smoothing methods as seen to the left. Using 80 datasets grouped into 13 categories with examples to the right. We evaluate these methods and data across all visual analytics tasks that I mentioned earlier. I'll now discuss some specific results, in this case for the retrieve value and determine range tasks. The overall best performing method was Gaussian smoothing. However, it wasn't the best method for all data. It tended to do best with data that had long-term or cyclical trends within it, as seen to the left. The second best method was topology-based smoothing, which tended to perform best on data with spiky features, as seen in the highlighted datasets to the left. Finally, the third best method overall was Savitsky-Golay, which performed best only with a single specific data type, that being the EEG data that we tested against. Here we see another example for the task of computing a derived value. This task had a single universal winner, which was the low-pass cutoff filter. It performed the best on all data types tested. The second best method overall was the topology-based smoothing, which performed second best for all except 2 datasets. Of course, these examples have covered just 3 of the 8 tasks that we analyzed. The remaining are, of course, enumerated in our paper. To better inform visualization design decisions, we also provide an overall grade for all 12 methods for each of the 8 tasks. The methods essentially fell into 3 groups: those which are good in general, those which are good for specific tasks, and those which should be avoided in most cases. In terms of overall good performers, we found that Gaussian smoothing performed admirably for data, in particular with long-term or cyclical trends, while the topology-based method performed particularly well on data with spiky features across all tasks. Nevertheless, either of these methods, in general, is a good default choice. We also identified a few methods, including Safitsky-Golay, low-pass cutoff filters, and the Douglas-Poiker method that performed well for specific tasks, often better than the Gaussian or topology-based smoothing on the same task. For example, with the find extrema and find anomalies tasks, the Douglas-Poiker method was the single most effective technique. Therefore, if this task is critical to your analysis, using Douglas-Poiker should be considered. Finally, we identified 7 methods that rarely performed well, indicating that they should only be used if you have a very specific reason to do so, perhaps having to do with the features of focus in the data or the high-level analytical task being performed. Of particular note in this group is uniform subsampling, which is a commonly used data reduction method, also commonly used for its smoothing side effects. Our results show that using it for smoothing is ill-advised, as it produced unreliable results that preserve no particular feature of the data. In conclusion, through building and testing our framework, we did find that no single smoothing technique was ideal for all types of data or all visual analytics tasks. Furthermore, we note that the choice of smoothing methods can have a significant impact on how data are distorted, and thus how they may be perceived by an end user. For the best results in your visualization, our framework can be used to analyze and select the most effective smoothing method for your specific dataset and tasks. However, if that isn't an option, you can at least use our findings to make a reasonable choice of which method to use for your specific scenario. To view a demo of our framework, please see the link to the right. I'd like to thank you for your attention. To the right, you'll find links to our code, data, and paper, and I would be happy to take any questions.
All right, let's everybody thank Paul for a great presentation. Now, my first question for you is, can you give us a teaser of those 4 classes of line chart smoothing that you described in the paper but weren't able to get to in the talk?
Absolutely. So I'm actually going to say, instead of 4, there are really 2 main ones that are important, and those really break down to methods that operate locally and those that operate globally. So local ones tend to take a window of data and do some kind of smoothing within that window. So a Gaussian is an example of a local method. And then there are the global ones, which consider all of the data. And so something like doing an FFT on your data would be a global technique. It's going to retain, it's going to analyze signals from or analyze frequencies from the entire data set.
You also mentioned in the paper that the aesthetics of these approaches can be quite different, which we also saw from the figures in your presentation. Like the topology-based smoothing is pretty spiky and the Gaussian-based smoothing is quite smooth. Can you elaborate on how these aesthetic differences could affect what users are able to perceive? And can you think of any way to help quantify the effect of these?
Yeah, so I think I can only speculate because we did actually study this, but I could say that the Gaussian techniques, being that they were smoother, if you were wanting to do something like pick a peak, it might be a little bit more difficult because you get this small derivative as you approach that peak. Whereas with the topology-based method, as an example, you get this spike that's a very obvious spike. So I think, just guessing, something, it would have to do something with the derivative of the space would maybe give you an indication as to what's more useful. But again, that's just mostly speculation.
We have one more question in the chat, but we don't have time left for it. So everybody thank Paul again.
Thank you.
Our next presentation is by Angelos Katibarbas, and it's on StackGenVis, alignment of data, algorithms, and models for stacking ensemble learning using performance metrics.
Hello everyone, my name is Angelos Katibarbas. I'm a PhD student at Linnaeus University, Sweden, and I'm here to present our paper entitled StackGenVis, alignment of data, algorithms, and models for stacking ensemble learning using performance metrics. This work is a collaboration with my colleagues Rafael Martins, Kostadin Kutzer, and Andreas Keren from Linnaeus University. We will start with a brief discussion of the motivation for our work and the related research that we found. Then we present the details with regard to the functionalities of the system, and at the same time we describe the first use case with the goal of improving another stacking ensembles results for healthcare data. Afterwards, I will briefly mention the application of our system for the task of stance detection in text retrieved from social media. The results show improvement in the process of composing stacking ensembles and improvement in the performance based on multiple validation metrics. Then we have the presentation of qualitative results of expert interviews we performed, which showed promising results. And finally, I will finish with a discussion of limitations and future work opportunities we identified. Let's start with a short definition of what is stacking ensemble learning. It is an ensemble method that combines heterogeneous base models, arranges these models in at least one layer, employs another meta model, which summarizes the predictions of those models, resulting in improved predictive power. Although stacking may be a highly effective approach for increasing the predictive performance of machine learning, generating a stack of models from scratch can be a cumbersome trial and error process. This challenge stems from the enormous space of available solutions, with different sets of data instances and features that could be used for training, several algorithms to choose from, and instantiations of these algorithms using diverse parameters, in other words, models, that perform differently according to various metrics. There are several existing visual analytics approaches, tools, and systems developed for bagging, boosting, and buckets of models, but not stacking. BEAMS focuses on regression tasks, and it includes 4 learning algorithms and a model sampling technique. The system produces a ranking that helps a user to decide on a model. In our approach, a meta model automatically chooses well-performing models. Interestingly, the authors mention an open question of how best to compare multiple models directly. In our system, we address this challenge with the exploration of a finite space of solutions employing multiple algorithms. Manifold generates pairs of models and compares them over all classes of a dataset, including feature selection. We adopt a similar approach, but instead of comparing a large number of models in a pairwise manner, we aggregate their overall and per class performance. Then, the user can compare a set of models against the average of all the models before deciding which ones to use. We adapted the knowledge generation model in visual analytics from Sehi and others specifically for ensemble learning. Further details can be found in the paper. According to the modified knowledge generation model, we designed StackGenVis, which is our proposed visual analytics system that allows the user to construct and interact with stacking ensembles for the given input data. It comprises the following workflow: the selection of appropriate validation metrics, the exploration of algorithms, the data wrangling, the exploration of models, and an overarching phase where the resulting stack is traced and the performance of the stored stack is compared to the current active meta model. This is an iterative process with a final composition of the most performant, most diverse, and simplest stack. The generated knowledge is fed back to the user, helping to increase their trust in the results. The user can stop when their expectations are met. The video demonstration presents a use case based on the heart disease dataset. It showcases the main components of the system and the real-world application. Xinhuan Shu uses multiple performance metrics which can be combined into one single measurement with different weights for increasing trust in the results. In our case, as our dataset contains balanced healthcare data, we ignore validation metrics such as Jaemin and Thu Oct, and we choose to focus on the false negative cases with the F2 score metric. As we want to bias our metric towards the disease class, hence, we use microaverage. All the models of all algorithms are then sorted according to the new settings of the performance metric. We select to resort the models based on the most performant for this class, and we start our exploration by picking the KNN algorithm. From the most performant models, we select those having from 15 to 20 number of neighbors, the Minkowski metric, and the bold tree algorithm. As a result, the per-class performance for this algorithm is greater than the average sum for all the KNN models. We continue with the selection of models from other algorithms. 6 different algorithms and 204 models with diverse parameters are included in the initial stack. In the overview of the algorithm space, we can observe the percentage of the chosen models for every algorithm compared to the entire explorable space provided by the system. With all the algorithms and hyperparameters in place, we execute the stacking ensemble for the first time. The resulting stack is shown at the top with models represented as points and color encoding used for the different previously selected algorithms. The radial chart summarizes the accuracy, precision, recall, and F1 score results. The data space consists on a TSNE projection of the data and a parallel coordinates plot showing the features. Here the analyst can modify the dataset if necessary, for example by merging, composing, or removing instances. According to the dataset we have, the CA attribute has values ranging from 0 to 3. However, we can observe a 4 in the parallel coordinates plot, where all the unknown values were gathered. Thus, we decide to pick them and then remove the data point. That appears to cause troubles to the entire stack's predictive results. The view to the right shows the importance of each attribute for each model in the stack, computed from a combination of 3 different approaches of feature selection. The normalized importance values are mapped to colors according to the legend. Initially, all the models look very similar, with only differences for each attribute. After disabling univariate feature selection, we see that 3 out of 13 attributes could be unselected, based on their low overall importance for the models. We update the active meta model's performance, and since it has increased, we choose to save the new stack. The model space view shows an MDS projection of all the models in the stack, such that models with similar performance across different metrics are positioned closer to each other. Here we try to find models that could be removed without reducing the performance in order to decrease the complexity of our stack. Indeed, if we check the accuracy, F2 score, and Matthews correlation coefficient validation metrics separately, we are able to judge which models could be removed because they perform in a somewhat similar way. After the filtering, the performance remained the same, but we have 25 fewer models in our final stack. We decide then to store the new stacking ensemble. The prediction space is the last step of the investigation of our stacking ensemble. This projection shows us how similar are the predictions for the data instances across all models of the stack. Compact groups of points, such as this and that, indicate groups of instances that were consistently predicted to be in the same class. On the other hand, points in between the groups, such as here or there, indicate that Different models in the stack are resulting in conflicting predictions for these instances. The histogram's y-axis shows the number of models, and the x-axis the performance from 0 to 100%. While selecting a couple of data points, we could see in the histogram that no additional model would perform better for this subset of data points. Indeed, the gray bars for the selection are to the left of the bars in black, showing the average performance of all models. Therefore, we decided to stop doing any additional actions. If desired, we have the option to go back in time and choose a previous snapshot of the stack, such as the third ensemble, leading to an iterative procedure of exploring new undiscovered paths. In this use case, we focus on stance detection in text data, more specifically, the category of hypotheticality. We applied our resulting meta-model to the same test data as Kepstead and others, and we were able to heavily improve the results from that paper. For more details, we refer the interested listener to our paper. 3 machine learning experts evaluated Xinhuan in individual 1-hour interview sessions. The feedback was related to the following aspects: workflow, visualization and interaction, limitations. All in all, the feedback was remarkably positive and encouraging with the choices we took during the development of Xinhuan. For instance, all experts agreed that the workflow of Xinhuan made sense. They all suggested that data wrangling could happen before the algorithm's exploration. However, they also mentioned that it is usual to first train a few algorithms and then, based on their predictions, wrangle the data. In another example, 2 out of the 3 experts were positively surprised by the power of visualization regarding the possibilities of dynamically and directly interacting with the machine learning algorithms and models. Complex ensemble learning methods require a lot of computational resources, which affects the performance of our approach. Also, the use of visual analytics in between levels makes this even worse. Progressive visual analytics workflows could be useful for improving the scalability of our approach for larger datasets. Interpretability and explainability is another challenge in complicated ensemble methods, which is not necessarily always a problem depending on the data and the tasks. Utilization of user-selected weights for multiple validation metrics is one way towards addressing this challenge. Support for multiple layers of stacking is set as another future work goal. While the experts mentioned that they typically use a single layer of models in their practice, we can investigate the adaptations for more layers required for our workflow. We still need to investigate further the impact of alternative meta-models on the predictive performance, and try out different modifications of stacking, for instance by adapting our workflow with an extra step of visually comparing various meta-models. All in all, these limitations constitute possible direction for future work. That was it from my side. Thank you all for your attention, and remember to visit the links below for accessing the paper, testing the tool online, watching the demonstration video, and tweaking the code of Xinhuan.
Let's everyone thank Angelos for a great presentation. Kiro Hennessy on YouTube asks which UI libraries or frameworks are used as part of StackGenViz.
Yeah, thank you very much for the nice question. I have used Vue.js, D3.js for the visualization, and also Plotly.js.
I have a question for you. Would you in general recommend trying out stacking ensemble learning for someone who has not previously used ensemble learning at all, or perhaps used a different ensemble learning strategy like boosting or bagging?
Thank you very much for this interesting question. In short, my answer would be yes. I suggest everyone that has not used stacking ensemble yet to give it a try, especially with a visual analytics system such as Xinhuan. The process should be straightforward compared to other approaches, for example, because users receive visual feedback while making decisions. Also, they could avoid trial and error processes, which is quite common when building stacking ensembles from scratch. Of course, in the second part of your question, if we have machine learning experts or people that have used ensemble learning methods in the past, then of course it's very much more easy actually to understand
the underlying concepts of Stacks and VIS.
Another question for you. What happens when users have finished working within StackGen Viz? They're happy with their ensembles. What do they do next? Is it possible for them to use ensembles for previously unseen data or export trained models somehow to be used elsewhere?
Thank you very much for this nice question. Stacks and VIS is actually more than a prototype. So it's not simply a prototype tool. It enables users to export the knowledge they have acquired from the visual analysis that they have already done with our tool. So it allows the users more or less to extract the models that compose the final constructed ensemble that met their expectations. So in this way, we can say that people could deploy the stacking ensemble in a powerful server and then test with external validation data in real world scenarios, of course.
Thank you very much, Angelos.
Thank you very much.
Now, let's all thank all of our wonderful authors for their presentations this session, as well as the viewers for their compliments that we didn't even talk about on the live stream, and the great discussion that they've had on Discord.
Thank you.
To interactively explore and visually analyze large multivariate data. For example, this cosmological simulation that is clustered into dark matter halos. We create a probabilistic data model in each cluster. We present a complete visual analysis system based on this data representation, which is especially well suited for the density-based visualizations shown here.
We present AgentViz, an application for the visual analysis of call center agent behavior using hierarchical glyphs. Our application relies on a data-driven scatterplot layout, with each glyph representing an individual call center agent. We demonstrate the application with nearly 5 million calls who interact with over 6,500 call center agents. To reduce clutter, we present a dynamic aggregating glyph clustering technique that varies with zoom level, maximizing the screen space.
What do you believe is the correlation between labor union participation and corporate profits of different companies? How would you update your belief after seeing this scatter plot? In this study, we use a new elicitation technique to understand how people update their beliefs about correlations after seeing different visualizations with and without uncertainty depictions.
Many techniques can be used to render and visually explore large 3D line sets with transparency. However, all these techniques differ in several aspects such as runtime performance, memory consumption, and image quality. In this work, we provide an extensive comparison study to discuss the advantages and drawbacks of transparency rendering techniques for large line datasets.
Language models are highly performant across many language understanding tasks. Comprehending the linguistic knowledge encoded by these models, however, remains a challenging problem. We introduced an approach for visually analyzing contextualized embeddings produced by language models. Our design shows how much context is captured by embeddings, the ability of embeddings to capture meaningful text spans, and linguistic relationships represented by the embeddings.
It is common for users to struggle to understand how to effectively use TS&E. No idea how to select hyperparameters, assess the quality of the results, investigate the existence of shapes and other patterns. TVS&E covers all these tasks. We provide diverse projections to choose from, global and local quality assessment, investigations of shapes and patterns, and more.
Hey everyone, I'm Xinhuan Shu, a PhD candidate at Purdue University, computer graphics major, and a research internship at Bach Research North America. Here, we are presenting our recent research, Persevere, using factorized prototypes to visually interpret and diagnose deep neural network. This work is co-authored by research scientists at Bosch, Zeng, Dr. Xinhuan Shu, and Dr. Liu Ren.
We present an efficient approach for volume and isosurface ray tracing of structured AMR data on GPU-equipped workstations, using a combination of two different data structures. Together, these data structures allow a ray tracing-based renderer to quickly determine which segments along the ray need to be integrated and at what frequency, while also providing quick access to all data values required for a smooth sample reconstruction kernel.
Region-based vortex measures are commonly used to extract vortices. The ideal threshold to extract the vortex boundary, however, varies spatially. To detect vortices without manual thresholding, we utilize supervised deep learning. For the regression, we evaluate 3 recent network architectures. The resulting networks are able to detect vortices that grow in size due to diffusion, despite their angular momentum becoming smaller.
We present an interface to visually analyze and steer zero-shot learning models. Our interface is designed to diagnose attribute mispredictions to convey potential failure modes in zero-shot learning. Using our interface, the user can select multiple categories for analysis. We allow the user to steer the model by changing the weights of potentially problematic attributes based on their analysis.
We introduce a direct volume rendering approach that can render encrypted images directly from encrypted datasets. The rendering is performed by operations in the encrypted number space, which are dual to operations in the plaintext space. Therefore, the rendering system does not need to decrypt the data. This homomorphic volume rendering approach makes it possible to use untrusted servers for rendering without compromising privacy.
VIS has been successfully helping not only experts but also people who want to learn about AI. At VAS 2018, we presented GANLab, an interactive tool for learning about a deep learning model called GAN. But how does VIS help these learners? We conducted 2 evaluation studies, including log analysis of our demo used by over 100,000 people. We will be sharing our findings with you.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
The transmission of pathogens such as bacteria and viruses is an acute problem in hospitals around the world. Infection control experts need to monitor infections and determine transmission pathways. We developed a novel visual analytics system for the exploration of disease outbreaks. It combines several interactive views and a tracing interaction that allows to detect pathogen transmissions.
Data stakeholders are rarely the data experts. Making tools for them means considering how they communicate about data. Rules are a convenient way for humans to express patterns in data, like we need high variable x and low variable y. In our human-in-the-loop approach, the user selects points of interest and can immediately see rules that differentiate those data from the rest. Lots more detail in the paper, even though it's short.
We proposed a multi-perspective simultaneous embedding (MPSE) algorithm for visualizing high-dimensional data based on multiple pairwise distances between the data points. MPSE computes positions for the points in 3D and provides different views into the data by means of 2D projections that preserve each of the given distance matrices. MPSE works on abstract data as well as graphs.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau, answer questions at the speed of thought.
Visualizing the performance progression of machine learning techniques is often achieved by plotting the accuracy in a line chart. For specific tasks such as multi-class classification, they hide important factors such as inner-class confusion and instance-level details. We propose Instance Flow, a tool for interactive visualization of the evolution of classifier confusion on the instance level.
We present a high-quality tube rendering method for 3D line datasets. GPU-based raycasting is used to render line segments as rounded cones, to allow for smooth connections along individual lines and variation in radius. We support transparency by a novel approach combining visibility order rendering with an order-independent transparency method. To improve depth and feature perception, ambient occlusion is employed.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau, answer questions at the speed of thought. Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau, answer questions at the speed of thought.
The mixture graph is a data structure for compressing, rendering, and querying segmented volumes. Biomedical segmentations have evolved from mere annotations to first-class modalities. The mixture graph stores the computations required to render such nominal data directly on the GPU, including pre-filtering and lighting. Segment distributions can be queried efficiently using regions of interest.
Taximis is an interactive visual analytic system to help tax officers identify suspicious tax evasion groups. The system integrates the traditional data mining algorithm and visual analytics techniques. 4 coordinate views are provided to support interactive exploration of tax evasion evidence. We demonstrate its usefulness through case studies using real-world test data and expert interviews.
Firstly, we extract contours of virions and distribution of spike proteins. From a newly estimated contour, a 3D mesh with evaluated triangles is obtained. In the last step, rules describing relations between protein instances are defined by the user. The resulting model is created by application of all rules on the generated 3D mesh.
How do user interactions lead to insights? We present a case study with a tool that supports 5 types of interactions for exploring drug-target relations. Through an evaluation, we collected interaction trails, manually extracted interaction patterns, characterized the user insights, and explored the relations between interactions and insights.
There are many similarities between visual analytics and interactive optimization. The design of visual interfaces for optimization systems is an application of visual analytics. However, many optimization systems are automated. If you are thinking of building an interactive optimization system, come to our talk. We have prepared some tips for you.
We present a framework for the visual exploration of spine simulation data. We show the force distribution on spinal discs, enable assessments of imbalances, and reveal impact vectors that were not accessible before. This is a novel direction in medical visualization, and we hope that it might bridge the gap between biomechanical research and clinical application.
In cancer research, it's useful to group patients based on disease spread patterns to the lymph nodes. But once we create a new clustering methodology using spatial data, how do we explain spatial clustering to non-experts? In this multi-year project, we dealt with both a participatory design stage and a broader dissemination stage, and distilled specific lessons for interpreting spatial clusters.
Different sampling strategies have different performances in preserving features, but which one is the best? In this paper, we selected 7 sampling strategies along with 8 representative datasets and 3 important visual factors. We formulated 4 hypotheses and conducted a user study with 100 participants. For the derived insights, please refer to our paper.
Traditional flow visualization methods, such as line integral convolution, convey information about the underlying flow structure. However, the influence of regions in the flow on each other is not visualized. In my talk, I will present a new dense flow visualization technique, creating a multi-level hierarchy that provides insight into the region's connectivity using a probabilistic model. For more specific details, come to my talk.
Given a dimensionality reduction scatterplot, we project its original subspace. Through the orientation and shape of our glyphs, both the global trends and local patterns can be identified. To transform the vectors, we use implicit function theorem. We apply our method to different kinds of data.
We present our work on data visualization, a technique which helps facilitate understanding of physical measurements and quantities by providing visible experiences to users in virtual reality. This allows them to experience the ground truth of what the data is in reality, as compared to the abstract nature of conventional data visualization. We hope our work will spur new considerations into how immersive technologies can be used for visualizing information, and that you will find it interesting.